Dear student, this is our third class, third lecture for the chapter partial differential equation. And in this class, in this lecture, we will discuss or we will be learning about the following topics. Number one is different form of wave equation, then solution of wave equations, first in one-dimensional Cartesian coordinate, and then two-dimensional Cartesian form or Cartesian coordinates, rectangular membrane for case of rectangular membrane, and then two-dimensional polar coordinates. In the practical case is vibration of circular membrane. For this case, the wave equation will be solved. After that, three-dimensional Cartesian coordinates, then three-dimensional spherical coordinates, and finally three-dimensional cylindrical coordinates. So in this lecture or in this class, we will solve basically the wave equation in all its forms. So let us now begin with the first topic, that is wave equation, and we know that the well-known wave equation is given by del u del t square is equal to c square del u del x square, where c is the constant having the dimension of velocity. You know that c is the velocity of the wave that is propagated through a medium, t being the time and x being the coordinate with respect to a certain reference frame. Now, U is an entity which may be mechanical displacement or potential for the flow. The above equation represents the propagation of plane wave with large amplitude, and equation 1 is the wave equation in one-dimensional case. Okay, and now in case of two-dimensional cases, the wave equation takes the form del to u del t square, that is equal to c square del to u del x square plus del to u del y square. And in case of three-dimensional cases, the wave equation can be represented by del to u by del t square c square into del to u del x square plus del to u del y square plus del to u del z square. So these are the three different forms in three-dimensional cases, the wave equation. And we understand from these three forms, basically, especially from the last or third or the three-dimensional form, that in three-dimensional cases, the propagation of wave function does not depend only on the space variables, that is x, y, z, but also on the time. That is, in this case, the variables are 4. So to solve this equation in three-dimensional cases or two-dimensional cases or one-dimensional cases, we have an extra variable compared to that of the Laplace's equations. So now we are here to solve the wave equation. For first case, we will solve the wave equation in one-dimensional cases and using separation of variables method. As I stated before, that the one-dimensional wave equation can be represented by the equation del to u del t square plus c is equal to c square del to u del x square. And to solve this equation, just separate variables and consider that u is equal to uxt. And then uxt is taken as x function of x and t function of t, and we are very familiar what to do in the separation of variable method, and we discussed much more in the just previous lecture. So in this case, we will not discuss all things, but consider that some things will be known, some things are known. Okay. So now first come to the fact that here del u del t is find out, and then del u del t square, that is this, and similarly del u del x square is this here. Just now substitute these values in this equation, you will have this. Okay, just substitute this, and then dividing by c square xt both sides of this equation, that will give you this one by c square t d2t by dt square, that is 1 by x d2x by dx square. So in this case, so the variables are therefore separated, and each term of this equation we know from our early knowledge, that is the knowledge from lecture number 2, that all these terms, all these terms will be equal and constant. Let's say this constant is lambda. So from first one, from this one you can write del 2x by del x square d2x by dx square is equal to lambda x. And from this one you can write d2t dt square c square lambda t. Now consider the following cases. Here we are here to consider some boundary conditions. Number one is when lambda is equal to 0. Not this boundary condition, but this some special cases. Number one is when lambda is equal to 0. If lambda is equal to 0, then del 2x by del x square is equal to, and from here you can write dx by this is d2x by dx square is equal to 0. From here you can write dx by dx is equal to constant. It should be constant, and from here dx is equal to a dx, and after integration you get ax plus b. Obviously here a and b are constants. And similarly from the second case you also find out the solution as y is equal to, from here is this is the, if lambda is equal to 0, then you can get ct plus d. So the complete solution in this case is u function of xt, that is equal to ax plus b into ct plus b. This is one solution. C and d are also constants. Now if you consider that lambda is equal to mu square, then from then you can obtain as one of the ordinary equation as d2x by dx square is equal to mu square x, and from here there is the process to solve this equation, and you see here from that m has to be plus minus mu, and then you know that this will give you a solution a to the power mu x plus b to the minus mu x. And from another term is here, another part is here, dqt by dt square is c square mu square t, and that will give you this that is equal to 0, and this equation will give you a solution of t is equal to b to the c mu t plus a t to the minus mu c t. So the complete solution is this into this, that is a to the mu x plus b to the minus mu x, b to the power, it can be written as c, so it is better to write c to the power mu ct plus d to the minus mu ct, because all a, b, c, d all are arbitrary constants, so there will be no problem in that. So when number 3 is when lambda is equal to minus mu square, then what will happen? D2x by dx square is equal to this, and this will give you there in this manner, and know that in this case then we will have two values plus minus I mu, and that will give you cos theta, cos or sin theta term. So x is equal to from here x is obtained as a cos mu x plus b sin mu x. Another one is d2 t by dt square is equal to minus c square mu square t, and that will give you a solution c cos mu ct plus d sin mu ct. So from here the complete solution will be mu x is equal to a cos mu x plus b sin mu x, c cos mu ct plus d sin mu ct. This is equation number 5, and you know the technique to solve all this, so I am not discussing in detail, just the solutions are here taken here. Now we consider the following boundary conditions, that is the boundary condition with which we can solve the values or find out the values of a, b, c, d. That is, to find out the values of arbitrary constants, you have to be you have some boundary conditions. So you have to some boundary conditions, and these are here, so that you x when x is equal to 0 at t is equal to 0, and when x is equal to l, t that is equal to 0, l is the value of x, and if x and t is equal to 0, then find it is a function of fx, and when del u del t at t is equal to 0 is equal to phi x. Just these are the boundary conditions, and we wish to apply these conditions. Now for the solution uxt that was taken for the first case, that is in which we have taken the constant as lambda, that is in this case, that is 3 cases we have discussed, that is in this case uxt is equal to ax plus b into ct plus d, that is considered here, that is here. Okay, for lambda is equal to 0. So where we know that already, find out that ax is equal to this and t is equal to this. Now from the boundary condition number 1, that is mu 0 t is equal to 0, that for x equal to 0, in that case we get x 0 and t function of t that is equal to 0, and from here either x 0 is 0 or t function of t is equal to 0. We understand it can be easily understood. Now from boundary condition 2, that is mu l t for the value of x at l and t is equal to 0, and from this relation, that is this that means from this expression you can write xl t is equal to 0, because in this, for the first case we have obtained that t is 0. In that case we also obtain xl is equal to 0. Okay, So XL is equal to 0 or XL is equal to 0. Both first case XL x of 0 was 0. Then XL for value of x at L, that was also 0, and T functionality at 0. So all these things are 0. So in that case, if you use x0, then for x equal to 0 from this relation x0 is equal to a into 0 plus b. That is here, and from here b is equal to 0, and up here also from this relation for the value of x equal to l, xl, that is here, that is equal to a into l plus b, and since b equal to 0 and xl is equal to 0, so from here a is equal to also 0, so a and b both are 0. And now from equation 4, so in this case we obtain that both a and b all are 0. Now from again from equation 4, that was done where the equation 4 was here. This is the equation 4, that a uxt was a e to the power mu x plus b to the minus mu x, that is here. That is also written here. That is uxt equal to a to the power mu x plus b to the minus mu x, c e to the power mu ct plus d to the minus mu ct. And using the boundary condition number 1, that is at x equal to 0, x0 is equal to, from here you obtain is x is equal to, if x is equal to 0, then a plus b, that is from here a and here b into this term is equal to 0, or a plus b is equal to 0, or a is equal to minus b from here, and at x equal to 0, so x is equal to, this is done here, and for x is equal to l, that is x is equal to l is equal to, from here you obtain a e to the power mu l plus b to the minus mu l, that into this term, that is equal to 0, because the value of xl is equal to 0. So from the boundary condition number 2. So from here you can easily understood that a e to the power mu l plus b to the minus mu l is equal to 0. Or here a is equal to 0, b equal to 0, because from here you can easily understand that a is equal to 0 because this term is not equal to 0. And since a is equal to 0, from here b is also equal to 0. Here, hence, what were the value of t function of t from here, since a and b is equal to 0, so u xt, you know that is x function of x and t function of t. Since x function of x is equal to 0 for, because of a and b is equal to 0, so this will give you null, that is u xt is equal to 0. So this solution, using the boundary condition, this solution fails to give the solution of the given problem. So this solution is not applicable. Now the rest one is equation number 5. So remember that for the first case, in this case also, in the first case, that is in the first case also a and b both becomes equal to 0, and in the similar manner that is explained here, that ux is equal to x t t. So irrespective of the value of t, since a and b are 0, so xx is equal to 0 for the first two solutions. So first two solutions do not give you the solution of the given problem. So only thing is that the last one is here, a cos mu x plus b sin mu x into c cos mu ct plus d sin mu ct. And now applying the boundary condition number 1, you know that u at the boundary condition number 1, that is u0, that is what was the boundary condition number 1? Here is the boundary condition number 1. u0t is equal to 0, that is for x equal to 0. That is here, that is done here, that is done here, that is done here. That is u0t for x equal to 0, that was 0. That is equal to, from here a, because from here you can cos mu 0, that will cos 0, that will give you a, and from here that will give you 0. So a into this term. Okay, this term is there. And since it is equal to 0 and this term not equal to 0, you can easily say that a is equal to 0. Now from the boundary condition number 2, that was dealt about that was given as mu l t is equal to 0. Just use the value of l, okay, x and l. Since a is equal to 0 for the first case, in this case it has been proved, so this term will not be there. So only term is this. So here it is there b sin and mu l is instead of x, so b sin mu l, and this term is here, that will be 0. So from here, since this term is not equal to 0, so sin mu l is equal to 0, and from here sin mu is equal to n pi by n, because this is equal to 0, that is sin n pi, n is equal to 1, 2, etc. So from here mu is equal to n pi by l. So you can finally obtain from this expression that mu xt is equal to a is since a is 0, so this term will not be there, so that the rest part will be b sin mu x into c cos mu ct d sin mu ct, and now here the value of mu, so that is equal to sin n by x by L, and this b and this c when multiplied, that give you another arbitrary constant c prime, and then c prime cos n pi c t by L plus d prime sin n pi c t by L. D prime is nothing but this d and this d, and here just we have used the value of mu, so we get mu x is equal to this in this form. Now for all values of n, so if you consider all values of n, so you have to sum over this term. So that is there mu x is equal to n is equal to 1 to infinity this into this term is actually there. Now using the boundary condition number 3 that was given as mu ux0, that is equal to function of x. So from here you can write that is mu ux0 that is equal to fx, that is equal to, from here n is equal to 1 to infinity, okay, and then you see from this that in this case t is equal to 0, so cos this term will then from here you can write that also that sin x, okay, cn prime somewhere n is equal to 0 to infinity, and that is equal to cn prime sin n pi x by L, and because in this case t is equal to 0, so t equal to 0, then this term will give you 1, and this term, since it is sin term, so this one will give you 0. So essentially ux0 that is function of x, that is 0 to 1 to infinity cn prime sin n pi x. So just do this integration 0 to L fx sin n pi x by L dx, multiplying this term with this term, then integrating from 0 to L, that will be here. So first cn prime, okay, I am dividing here by 2, so here should be multiplied, and 0 to L this sin n pi x here and this sin n pi x here, so that will give you 2 sin square n pi x L dx. So if you integrate this will give you 2 sin n square pi x L dx, that will give you 1 minus cos 2 theta. You know that 2 sin square theta is 1 minus cos 2 theta, and if you integrate the cos term, that will give you sin term, and sin term will give you a null result from 0 to L. So only the term there will be the integration of dx from 0 to L, that will give you this cn prime by 2 and then L. So that is here. So from here cn prime is equal to 2 by L 0 to L fx sin n pi x by L dx. So therefore we here understand the value of c prime, calculated the value of c prime. Now boundary condition number 4, that was here, that is here, del u del t at t is equal to 0, that is equal to phi x. So from here just differentiate the value, just differentiate the value of u which was given in the equation, that is here, the equation is there, that is given here, this is there, this is let's differentiate this equation with respect to t. So that is here, that will give you del t is ddt of n equals 0 to infinity, and all these terms, all the terms are here, and then so del u del t is equal to n equal 1 to infinity, and just integrate, so differentiate this term is the constant term, so that is here, then cn prime here, and cos n pi ct by L, if you differentiate it, it will give you cos term, sin term, sorry, that is with a negative sign, that is here sin n pi ct L, and the differentiation of n pi ct L by L is give you n pi c by L, and differentiation of this is here. Sin theta will give you cos term, and the differentiation of n pi ct by L is equal to n pi c by L. So that will give you at t equal to 0, del u del t at t is equal to 0, use t equal to 0 in this expression. So that is here, n is equal to infinity, this sin n pi x by L is here, and from this c is equal to 0, so this term will give you null result, and from this you will have the term tn prime into n pi c by L. So that is here, t is tn prime n pi c by L, and this sin n pi x by L is equal to here, and that is phi x, that was given phi x. So now right hand side of this expression is the Fourier expansion of the function phi x, that is this term actually, this term. So from here you can write tn prime is equal to L this L by n pi c 0 to L phi x sin n pi x by L dx. Since this right hand side is nothing but this term is nothing but the Fourier expression of this term. So from here dn prime can be written. This type of finding out the constant dn prime is can be studied in the chapter Fourier series of Fourier expansion of functions. So this is here. So dn prime is calculated in this manner. So if we now use the value of dn prime and cn prime, we will have mu xt is equal to n is equal to infinity sin n pi x by L 2 by L 0 to infinity fx sin n pi x by L dx, then cos n pi ct L plus L by n pi c 0 to L n pi ct by L pi x sin n pi x L dx. Just use the value of cn prime and dn prime in this expression. Just write the value, substitute the values of cn prime and dn prime, then you will get this finally this expression. Now if we put phi x into 0 with the initial velocity, because when initial velocity is 0, then phi x will be 0, then this dn prime that is driven from this relation is equal to 0. So mu xt then will have the value because this term will be not there. This term, entire term will not be there. So only this term will be there, and just write it as in this fashion: half, then 2 will be multiplied here, n is equal to cn prime cos n pi ct by L sin n pi x by L. So that is can be written in the manner that n is equal to 1 cn prime by 2, this cn prime by 2 sin. This term can be written as 2 cos n pi ct by L into sin n pi x by L, that is 2 cos a sin b. That can be written as sin, or 2 sin a cos b. That can be written as sin a plus b and sin a minus b. That is sin n pi. This term is written first. Here is the term x and here is ct. So a is x and b is ct. So this term 2 sin n pi x by L cos n pi ct by L, that is in the form of 2 sin a cos b. That can be written as 2. That can be written as sin a plus b and sin a minus b. That is done. So that will give you n is equal to 1 to infinity cn prime by 2 sin n pi by L x is there minus ct. This is the minus term for, and this is the plus term for cn prime this. So this is the solution of one-dimensional equation wave equation, and in this case we have learned how to apply the boundary conditions, and using boundary conditions how can we find out or estimate find out the values of the arbitrary constants. So this is the final result, final solution of for uxt in Cartesian coordinate. Now come to the solution of two-dimensional wave equation in rectangular and polar coordinates. First, rectangular polar coordinates. This is nothing but rectangular membrane. So what is rectangular membrane? That is given, that is written here. We consider the transverse vibration of a uniform rectangular membrane. The membrane is considered as a flexible uniform lamina of solid matter having uniform thickness and thickness in all directions by a tension tau. Okay, so here is the definition. We consider the transverse vibration of a uniform rectangular membrane. What is the membrane now? The membrane is considered as a flexible and uniform lamina of solid matter having uniform thickness stressed in all directions by a tension tau, and let rho be the density of that membrane, and both tau and rho are constant. So from here we learn that what is a rectangular membrane. Rectangular membrane is considered a flexible one, and which is uniform lamina, and which is uniform in thickness and in all directions. So here the tension is taken as tau and rho be the density, and both of them are constants. So in that case, two-dimensional wave equation then can be given. We know that the two-dimensional wave equation is del 2u del t square, del 2u del t square c square, del 2u del x square plus del 2u del y square. In this case, obviously, this c square is tau y. rho. Now, now we impose that the boundary conditions of the membrane is that the membrane is formed in such a way that the coordinate axis and the lines, that is x equal to n and y equal to b, the value of u at every point on the boundary is 0. So in this case we employ, or we impose the boundary condition such that the, the the lamina, or that the membrane is formed by the coordinate axis, that is x axis and y axis, and the lines at x equal to a and y equal to b. Okay, and the value of u at every point of the boundary that is at x equal to 0, x equal to a, and y equal to 0, y equal to, because it is formed by the lines. One is by the coordinate axis, that is x axis and y axis, and further the line x equal to a and y equal to b. So the value of u at every point of the boundary, that is bounded membrane, that by the points x equal to 0, x equal to a, y equal to 0, y equal to b are 0. So for the boundary conditions, here u, here is x0, then yt is equal to 0. Here ux is equal to a, yt is equal to 0, ux y0 t is equal to 0, and ux b, y is b, here t is equal to 0. Also, the initial velocity and displacement are also given by, I have written this as equation of 2 and 3 as ux y at t equal to 0. The initial velocity is taken as fxy, function of xy, and differentiation of this with at t equal to 0, that is del u del t at t equal to 0 is equal to 5. This is another function of xy. Right, these are the initial displacement here. Okay, and velocity. This is the initial displacement and this is the initial velocity. These are the so here we obtain actually 4 and 6 boundary conditions, and now we are here we wish to apply all these boundary conditions in suitable cases. So here to solve the differential equation, partial differential equation of wave equation in two-dimensional partial coordinates, we have to use, or we have to write uxt, uxyt as x, y, and t. Obviously, from here it is very understandable. It is very much understandable that this is the function of x, this is the function of y, and this is the function of t. And in this section, I will not discuss in details. Okay, because we have already well practiced, well known with the methodology of separation of this type of equation. Okay, now from equation number 1, that was del 2u by del 2t square, that is equal to c square, del 2 x by del x square plus del 2u by del x square plus del 2u by del y square. From this relation, using this, we can write, substituting the values of del 2u by del t square, del 2x by u by del x square, and then del 2u by, that is this equation, nothing but this equation. Just say this equation. In this equation, substitute these values. So that will give you this. Okay, this. Now dividing both sides of this equation, finally we get this, because we know how to achieve this equation, obtain this equation. Okay, fine. Now and I know that all these terms will be constants, and this term will be another constant. Obviously, that should be the sum of these two terms. We know it. Why these are constants? So from number 1, this is the following case that to be studied. Number 1, when this term 1 by x d2x by dx is equal to 0. This is a case. So in this case, and in this case also, 1 by y d2y by dy square is equal to 0 also. And if these are 2 0, so this is also should be 0. And solving this, you get x equal to x a1x plus b, and y is equal to a2y plus b2, and t is equal to a3t plus b3. So it is no longer to say that ABC, all ABs are constants. This is equation number 5. Now another consideration is here. If you take 1 by x d2 x by dx is equal to lambda 1 square, and this 1 by y d2 y by dy is equal to lambda 2 square, and then 1 by c square t d2 t by dt square should be the sum of these lambda 1 square and lambda 2 square. That is, it is there lambda square, and this lambda square should be lambda square plus lambda 2 square to satisfy this equation. To satisfy here is the equation, these equations. Okay. Now, if you once do it, Then from here also we can find find out the solution as x. From here, from this one, x is equal to a1 e to the power lambda 1x plus b e to the power minus lambda 1x, and from here we similarly obtain the z e to the lambda 2y plus b e to the minus lambda 2y, and since it is lambda square, so in this case also we may also get t is equal to a3 e to the power lambda ct plus b3 e to the power minus lambda ct. All a's, b's and c's are arbitrary constants. And another case is there, if we consider that 1 by x into x by dx is equal to minus lambda 1 square, and this term is equal to minus lambda 2 square, then this term, that is 1 by c square t by t square, should also be, it is also equal to lambda square, and from here we can easily write lambda square to lambda square plus lambda 2 square. Okay, this is also from this you can write that 1 by t d2t by dt square, it is better to say write that 1 by t d2t by dt square is equal to lambda square c. So lambda square is also lambda square plus lambda 2 square, and it will be c square. So if here is if you write this lambda square as lambda square plus lambda 2 square into c square, then these will satisfy. And here also lambda square should be lambda square plus lambda square into c square. Here also it should be. Okay. Now the solution of first one, this one will, all these terms, see from here that all these terms will give you cos and sin terms. So x is equal to a1 cos lambda 1x plus b1 sin lambda 1x, and this will give you a2 cos lambda 2y plus b2 sin lambda 2y, and this will give you a3 cos lambda ct plus b3 sin lambda ct. So these are equation number 7. Now we are here to employ the boundary conditions. So for u, the first condition, that is u at x equal to 0 y t is equal to 0, just use the value x0 y t that is equal to 0, and from this you can write that either x is equal to 0 or y is equal to 0 or t is equal to 0. And the second one boundary condition is u a y t that is equal to 0, or from here x a y t is equal to 0, and since y t is equal to 0, so x is equal to 0. And after another condition u x 0 t, that is for y is equal to 0, from here you can understand that x here x function of x, then y function of y of 0, and t of t is equal to 0. From here easily you can also say that xx is equal to 0 or y0 is equal to 0, and t is equal to 0. And finally another condition is there u x bt. If you use here, if here xx then yb then tt is equal to 0, since we have already seen that xx and tt both are 0, so yb is equal to 0. So essentially we get from here that x0 is equal to 0, x is equal to 0, yb is equal to 0, y0 is equal to 0, and tt is equal to 0. So all these terms are 0. So the solution in this case cannot be achieved, cannot be found out by this relation, because here is the reason. Here is the reason for x is equal to 0. You know that for x is equal to 0, just use the value of x equal to 0 in this relation. Yeah. For the first case, that means in this relation. In this x is equal to 0. So x0, x function of 0, x0, x at 0, that is a1 into 0 plus b1. So from here you can write b1 is equal to 0, and that is here b1 is equal to 0. And when xa at x equal to a, you know that is also 0, then a1 plus b1 is equal to 0, or from here since b1 is equal to 0, so a1 should be 0. Similarly a2 and b2 are 0, and a3 and b3 all are 0. So every a1 b1 all a's and b's are 0. So this is done here also. Just go through this. So in this case the solution cannot be possible because all arbitrary constants are 0. So this will give you no result. So therefore the solution given by this equation that is here, these equations cannot be possible. Okay. So this is not this. So this solution is cancelled. There are two possibilities, that is this and this. Now to check whether which one of these are applicable or will will be considered. So that is there, that is done here, that is there. Okay. Now once we remember the rest two solutions, the rest two solutions are also here given. How in this case, so it just what we done in this case, what we did in this case, similar process you can employ, similar process for the second series of solutions. Then in this case you also find that all of A's and B's and C's, that is A1, B1, A2, B2, A3, B3, all are 0. You can also prove it in the similar way that I have done in these cases. So for that cases also the second solution, series of solution, the second series of solution cannot be possible also. So third, the remaining solutions are these. That is, yeah, that is it. So for first and second series of solution cannot possible, and we are here to check whether the third one is possible or not. The third solutions were here, were like this. These x is equal to a1 cos lambda 1x, b1 sin lambda 1x, then y is equal to a2 cos lambda 2y, b2 sin lambda 2y, tt is equal to a3 cos lambda ct plus b3 sin lambda ct. Now we apply the first boundary condition, that is u0 yt, that is equal to 0, where x0 is equal to 0. Now using this, if we use these values, then here x0 will be a1, then cos a1 into 0, a1 into 1, then b1 into 0, because this will give you 0. From here, therefore, you can find a1 is equal to 0. So this solution will give you x function of x is equal to b1 sin lambda 1x. Okay, this is equation number 8. Now the second condition, that is uayt, that is also 0, and henceforth you can easily directly write that xa, that will also be 0. Now use the value of x as a in this relation. That will give you, because not in this relation but in this relation, because a1 term, this term is not here. So xx is equal to this. So now since uayt is equal to 0, so x will also be 0. So that means xa is equal to 0, that is equal to b1 sin lambda 1a. That is here. So that is equal to sin m pi. M is constant, starting from 1 to 3, 1 to other higher values. So from here you can write lambda 1, calculate lambda 1 is equal to m pi by a. So from this relation, x is equal to b1 sin m pi x by a. Okay, you should remember this m is a constant which has value starting from 1 and goes to 2, 3, 4, etc. Okay, and you can also use m is constant. Okay, now go to the next one. Similarly, why that using the same process that we did here, you can also find out, you can also show that lambda 2 is equal to in the similar manner, since in this case lambda 1 is equal to m pi by a, there will be another constant integer, that is n. So similarly you can show that lambda 2 is equal to n pi by b. In this case also n is equal to 1, 2, 3, etc. So similar fashion, you can write yy, you can calculate yy is equal to b2 sin n pi y by b, and thus solution of two-dimensional equation becomes uxyt, that is equal to a3 cos lambda t plus b3 sin lambda t. That was the t term, the term consisting of the function t, and then for b1 sin n pi by ax, and then b2 sin n pi y by b. Just write it in here. Here is these are here. So uxy t is equal to a cos lambda t, because in this case just multiply b1, b2 and h, that will give you a cos lambda t, and further b1, b2 and these b3 will give you another constant b sin lambda t, and then this sin n pi x by a, then this sin n pi x by b. Okay, so these are also here, and you know that lambda square is equal to c square into lambda square 1 square plus lambda square, and from here that is equal to m square pi square c square by a plus n square pi square by b square. These are the value of lambda square. This is the. So if you consider all the values of m and n, then you should sum over this term. So then uxyt is equal to m1 to infinity n1 to infinity, then amn cos number t plus bmn sin number t, then the rest part sin m pi x by a sin n pi by b. So this is the complete solution in two-dimensional cases. Now also using the boundary condition given in equation 2, that is uxy0 at fxy. Then fxy will be can be written as, from this relation fxy can be written as m is equal to 1 to, because you know that uxy0 is equal to fxy. So you in using this relation, using t is equal to 0, from this relation you can write this fxy is equal to m is equal to 1 to infinity, n is equal to 1 to infinity, and since t is equal to 0, this term will give you this term will give you 0 result, and this term will give you only amn. So amn is here, and these two terms are here. So this is called the Fourier double sine series. This is called the Fourier double sine series. Now to find out the value of amn and bmn. So now just integrate this equation from 0 to a, 0 to b by multiplying sin m pi x by a, sin n pi y by, this will be b, then just first multiply this expression by sin n pi x by a into sin n pi y by, here is, it should be b, okay, it should be b, from 0 to a, 0 to b for x and y dx. That will give you 0 to a, 0 to b, this mn is here, there will be sin m pi m sin square m pi x by a, and the sin m pi x by a, and then sin square will be here, and then sin square n pi y by b dx dy. Okay, so that will give you, finally that will give you, if you know that from this equation you can write it to here multiply by 1 by 4, then 2 will this term 2 sin square m pi x by a, another 2 with this 2 sin square n pi y by b dx dy. And now you know that this 2 sin square m pi x by a can be written as 1 minus cos 2 m pi x by a, and this can also be written as 1 minus cos 2n pi y by b. So if you integrate, the integration of cos pi will give you actually sine terms, and sine terms will vanish in this limit. So there will be only the integration of 0 to a dx into 0 to b dy with the multiplication amn. So that will give you with 1/4. So that will give you amn by 4 into ab. Okay, so from here amn is equal to, the constant amn is equal to 4 by ab 0 to a 0 to b fxy sin n pi x by a sin n pi y by b dx dy. Now your job is to just okay, this is there. And another condition is that, another, just you find out the value of duxy by dt. So this is done here. Here is the constant term amn here, and this is the limit. Okay, then this will give you the term from where, from, you have to use this relation, use this relation. Amn will be there, then this will give minus sin lambda t, then lambda, okay, and from here plus bmn, this will cos lambda t, then lambda. So that are done here. Okay, this is there. A minus amn lambda amn minus amn lambda sin lambda t, okay, with the multiplication of lambda, then bmn lambda cos lambda t, and the rest part is there, are here. So that is, so and we also know that du t at t is equal to 0 is phi xy. So that is equal here phi xy, and that is equal to m is equal to 1 to infinity, n is equal to 1 to infinity. Here just in this expression write t is equal to 0. This will vanish, only this term will be there. So bmn sin m pi x by a sin n pi y by b. So sin m pi 1 by b. Okay. Now the similar manner, if you integrate this in the similar manner that we did in this case, that will provide you the value of this term is equal to lambda, this bmn by 4 into ab, and from here bmn is equal to 4 by lambda ab, 0 to a, 0 to b, phi ab, this term. Okay, here is written, that is written here. So now you have to and also the frequency of the vibration, and also lambda square is equal to m square per square square a square plus m square per square square b square, and from here lambda is equal to this. So lambda by 2 pi is equal to, you can write from here lambda by 2 pi is equal to c by this. This is this, okay. And now if m is equal to n, then lambda by 2 pi is equal to this. A and b, that is the free square membrane. For square membrane, lambda by 2 pi is equal to this. Just square something is here. That's using m is equal to n in this expression and is equal to b in this expression, just to be. These are the vibration frequencies of the vibrations. So we finally get the solutions of the two-dimensional wave equation as this, this. Okay. Obviously, this includes the value of AMN and BMN given here AMN and here is BN. So we here succeeded to find out the solution of solution of two-dimensional wave equation in Cartesian coordinates. Now let us go to the next one. So vibration of circular membrane, that is nothing but the membrane in case of two-dimensional polar coordinates, and that means in this case we have to solve the Laplace equation in two-dimensional polar coordinates. Okay, that is and in this case we know that this is the polar this is the two-dimensional Cartesian wave equation in two-dimensional Cartesian coordinates, and we know the transformation equation we already calculated. Just we use the value of the transformation of two-dimensional Laplace equation. Here is the derivation of the transformation equation. You need not to go through this because you already know that, and you have calculated all these things in our previous lecture. This is the calculations. It is done once again here, but you need not to calculate here once again because you already calculated this. Just only use this result. That is del 2u del x square plus del 2u del y square is equal to del 2u del r square plus 1 by r del u del r plus 1 by r square del 2u by del theta square. This is the two-dimensional. This is the Laplace equation in two-dimensional polar coordinates. Now from equation 1, that is from equation 1, that means from in this case, that is here from this equation you can write del 2u del t square to c square into this. That means you will have del 2u del t square to c square del 2u del r square plus 1 by r del u del r plus 1 by r square del 2u del theta square. This is equation number 3. To solve this equation, the method you will use the separation of variable methods, and we are not going all the things in details. Just you can write this u x y t can be converted into u r theta t, that is equal to this. Now just differentiate this with respect to r first, and then differentiate once again with respect to, so you will get this, and the value of d2u d theta square will be this, and d2u del t square is equal to this. Here is nothing nothing new. Already all of these things we have did in our previous cases. Now to substitution. Now the case come here to substitution of these values in equation. This equation now has reached to, now if we substitute these values in equation number 3, so then we will have this. Just substitute the values, and then we will have this. Now just divide both sides by r theta t into c square. That will give you this 1 by c square t d2 theta by dt square, dividing this equation by r theta d c square. So that will give you 1 by c square t d2 t by dt square is 1 by r d2 r by dr square plus 1 by r dr by dr plus 1 by r theta square theta square d2 theta by d theta square. And we know that all these terms should be constants, so that is equal to minus lambda square. You say it. So from here you also see that from in this the second hand term, right hand term, this term is independent of theta, so this term is constant, and since sum of these two terms is another constant, so this term should be another constant. So write it as this, take just 1 by theta d2 theta by d theta square is equal to constant, or it is better to say that all terms will be constant. So you write these equal to these equal to minus lambda square, okay, and then write this term except r square as constant, that is equal to minus n square. That is 1 by theta d to theta by d theta square is equal to n square. So from another relation is there, taking minus lambda square, that 1 by r d2 r by dr square plus 1 by r dr by dr minus, just use here the value of minus n square instead of 1 by theta d to theta by d theta square. That is here n square minus n square by r square, that is equal to minus lambda square. So that will give you 1 by r d2 r by dr square plus 1 by r dr by dr, that is equal to, just change the side of this term. So minus lambda square plus n square by r square, and that will give you 1 by d2 r by dr square plus 1 by r dr by dr plus lambda square minus n square lambda square into r is equal to 0. You can write it from this equation very easily. This is equation number 4. So this equation is nothing but the so-called famous, the well-known Bessel's equation, and it has the solution that can be given as r function of r, that is equal to a jn lambda r plus b yn lambda r, where a and b obviously are arbitrary constants, and this is the Bessel's function of first kind for the order n, and this is the Bessel's function of second kind for the order n. Also, as you have taken 1 by theta d to theta by d theta square is equal to minus n square. So from here you can write this equation, and after solving this, this will give you theta theta is equal to theta function theta is equal to c e to the power plus minus I n theta. That can also be written as c1 plus n theta plus c2 sin n theta. And also the left hand side, also from the left hand side, that is this term. This term is equal to this term, that is equal to minus lambda square. So this term is equal to minus lambda square. That is here. Minus lambda square. So from here, t2 t by dt square plus lambda square c square t is equal to 0. After solving this, you can obtain that t function t is equal to d e to the power plus minus I c t. So that can also be written as d1 cos lambda ct plus d2 sin lambda ct. So now taking all solutions for t, this t, and x, this t, then there and r and theta, you have obtained r q r theta t is equal to a, taking all values of a and t. So n is equal to 1 to infinity, n is equal to 1 to infinity, a m j n lambda plus b m y n lambda. This value is for the function capital R. And then this is the theta term c e to the power plus I n theta, and this is the t term including t. So d e to the power plus I lambda ct. So this is the complete solution of the Laplace's equation in two-dimensional polar coordinates. Now a boundary condition can be imposed on this. What is that? That is here. That is for the at the surface of the circular ring. That is r is equal to a. You can, because at the surface the value of u will be 0. That means a here, u here, then r theta phi was there. So it is a, then theta, then t is equal to 0. Now just write it r here function of a, then theta function, and t is equal to 0. And from since these are not 0, so you can write r a is equal to 0. Okay, because you know that at the surface of the medium u is equal to 0. So this gives you the result, and this should be equal, and this gives you the result a jn lambda a plus b yn lambda a, and this term will be 0 because for r when lambda, because yn lambda tends to infinity when r tends to 0. So this term will be 0, and that because since this term gives you 0, so you only have this term. So the complete solution is there. So nothing is being here. Just use this boundary condition. So now come to the next one, that is three-dimensional cases. So first three-dimensional wave equation in Cartesian coordinates. So in the Cartesian coordinates, we know that the wave equation is given by this. So to solve this equation, you obviously use here the situational variable method, and the boundary condition imposed on this are here: x is equal to 0 and x is equal to a, del u del x is equal to 0, at y is equal to 0, y is equal to b, del u del y is equal to 0, at z is equal to 0, z is equal to c, del u del z is equal to 0, and u x y z at t equal to 0, not in 0 obviously. Now this is here you can write ux, because in this case you see from this relation that u should be a function of x, y, z and t. So in trinomial cases the function you can be written in this way, and here the different values of the partial different derivatives involving in this relation. These are done here. These are find the values of different partial derivatives are found here, find here, calculated here, and then substitution of these values in this equation, that is the wave equation in three-dimensional cases, will provide you this 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 this. Okay. Now substitute. Now just multiply by dividing both sides of this equation by x, y, t, and c square. That will give you 1 by c square t, d2t by dt square plus 1 is equal to 1 by x, d2x by dx square plus 1 by y, d2y by dy square plus 1 by z, d2z by dz square. And it is not important, or it is not enough, that is it is not essential to remember you that all the terms will be constants, because you know it very well, that and we repeatedly used in our previous cases. So for the first case, consider this term that is 1 by lambda square, 1 by x is there, 1 by x, d2x by dx square. Mistakenly it is x square is given here. So 1 by x, d2x by dx square is equal to minus lambda x square. Okay, minus lambda x square. So from here you have a solution for x is equal to a to the plus I lambda x. That will provide you a1 cos lambda 1x plus b1 sin lambda 1x. Okay, it is fine. Now for the second one, that is 1 by y, d2yy. This is also 1 by y should be here. 1 by y, d2y by dy square. That will give you the solution, as because you know how to find out the solution. That will give you, this is a prime, so that will give you a double prime e to the I lambda 2y. Okay, so that can also be written as a2 cos lambda 2y plus b2 sin lambda 2y. And the third one is, that is 1 by z. 1 by z. This should be this term. This will be y. This will be z, not z square. Sorry, it is written mistakenly. So 1 by z, and it was 1 by y. So d2z by dz square is written minus lambda 3 square, and that will provide a solution, that is a3 cos lambda 3z plus b3 sin lambda 3z. That is equal to a triple prime, a 3 prime, a 2 prime, and e to the plus minus I lambda 3z. And finally 1 by c square t d2t by dt square is equal to, since y is written in this fashion, because you know that this term is lambda 1 square minus lambda square, this is minus lambda 2 square, this is minus lambda 3 square, so this should be minus of lambda square, and lambda square should be the sum of all these terms, that is lambda 1 square, lambda 2 square, and lambda 3 square. That is done here, that is written here. So here is that lambda square is equal to lambda 1 square plus lambda 2 square plus lambda 3 square in the next part. So from here from here you can write this is minus this, and this should be minus lambda square, because this lambda square is equal to all these three terms. So d2t by dt square plus lambda square c square t, from here negative sign will appear here. So from here you can write the solution of this. Solution of this is as a 4 prime e to the plus I lambda ct, that means a4 cos lambda ct plus d4 sin lambda ct. So therefore the general relation will be u x y z t is equal to, write these all things. First this term, just write all these three terms, this term, then into this term, then multiplied by this term, then multiplied by this term. That can also be written as this: a prime, double prime, it is this e to the plus I lambda 1x, lambda 2y, lambda 3z, lambda 3t, and that is can be written as a e to the plus I, and this, where a is the multiplication of these three terms, 4 terms. So we obtained here the solution of the Laplace equation in three-dimensional Cartesian coordinate. Now we have to use the boundary conditions. The boundary condition one that gives you that del u del x at x is equal to 0. So we just differentiate this equation. Differentiate this equation that will give you del u del x is equal to minus 1 lambda 1 sine, because this first term is here sine lambda 1 x plus lambda 1 b1 cos lambda 1 x and other terms. Just to differentiate this with respect to x, then these terms will give you these terms. Just differentiate. Nothing is difficult to do here. So then you know that del u del x at x equal to 0 is 0. That means this all these terms, and in this case use x equal to 0. So if this term, if we use x is equal to 0, so this term will give you 0 result, and from here we can write lambda 1 b1. That is lambda 1 b1, and all other terms are these, since these are independent of x. So then these lambda 1 b1 multiplied by all these terms will be 0, and all these terms, since all these terms are not equal to 0, so from here there you can write lambda 1 b1 is equal to 0 or b1 is equal to 0. So b1 is equal to 0 means this term will not be here. So in this expression this term will not be here. So from then another function, another boundary condition is here del u del x at x equal to a is also 0. So just write in this expression x is equal to a. So if you do that, a1 lambda 1 sine lambda 1 a. Okay, and since b1 is equal to 0, this term will not be there, and all these terms are constant. So from here you can write minus a1 lambda 1 sine lambda 1 a is equal to 0. Since lambda 1 not is equal to 0 and a1 not is equal to 0, you can write sine lambda 1 a is equal to 0, that is sine n pi, n is equal to 1 to 3, etc. Or here lambda 1 is equal to n1, right? It is as n1 pi. So lambda 1 is equal to n1 pi by a. And you can, if you use the, similarly, if you apply the boundary condition number 2, you can obtain that the next boundary condition. Then you can obtain that b2 is equal to 0, and similarly you can find lambda 2 is equal to n2 pi by b. And also, if you also boundary condition 3, you will provide you lambda 3 is equal to n3 pi by c and b3 equal to 0. In the similar process that is done in here and here, you can employ the similar process. Then you will, using the boundary condition 2, you will have b2 is equal to 0 and lambda 2 is equal to n2 pi by b, and lambda 3 is equal to n3 pi by c and b3 is equal to 0. Then lambda, you know that lambda is equal to lambda 1 square plus lambda 2 square plus lambda 3 square, that is equal to pi into n1 square by a square plus n2 square by b square plus n3 square by c square. Just substitute different values of lambdas in this expression. So then the solution takes the form u x y z t is equal to, that is here, and you know that this term, that is the term including this term is not there, so only the term these multiplying all these things. So that is done here. That is a1, a2, a3, a4 cos n1 pi x by a, cos n2 pi y by b, cos n3 pi z by c. Then cos this is there n square a square into n2 square by b square plus n3 square by c square into pi ct. Okay, it's pi ct. This c and this c are not equal, are not the same. Okay, so no, okay, a square b square c. This is the dimension. This is the dimension of the dimension in the z-axis. Z-axis. So, and this is the velocity of the wave. So finally, you get this. And then if a is equal to b equal to c, then you can have from this relation that all these a1, a2, a3, a4 will give you capital A, and just here use a. N1 pi x by a, cos n2 pi y by a, cos n3 pi by pi z by a, and then cos n squared n squared, then n2 squared, then n3 squared, then pi ct by. Okay, no problem is there. And now if you take all the values of n1, n2, n3, then the solution becomes x, y, z, t, n is equal to 1 to infinity, n2 is equal to 1 to infinity, n3 is equal to infinity. Just you have to write a, m, n1, n2, n3 instead of a, and then all these terms. These are done here. Now so the complete solution is this in the three-dimensional Cartesian coordinate. Now come to the spherical polar coordinates. You know that in case of spherical polar coordinates, the transformation equations are given by this, and the three-dimensional, and in that case the Cartesian and in that case the Laplace equation takes the form like this: del to u by del t square is equal to c square del, sorry, not a Laplace equation, it is a wave equation. So wave equation takes the form del to u by del t square is equal to c square del to u del r square by plus 2 by r del u del r plus 1 by r square del to u del theta square plus cot theta by r square del u del theta plus 1 by r square sin square theta del to u del phi square. This is equation number 1, and we will use variable method, separation of variable method to solve it. And so then you can write your theta phi t as this. And if you find out the values of del to u del t square and all the partial derivatives from this, and then substitute in this expression, then you will have this. Just do it, and then you will get this one. And then divide both sides by r theta phi t with c square. Then that will give you 1 by c square t d2 t by dt square. That is equal to 1 by r d2 r by dr square plus 2 by r dr by r plus 1 by r square theta d2 theta by d theta square plus cos theta by r square theta d theta by d small theta plus 1 by r square sin square theta, then phi, then d2 phi by d phi square. Okay, then you can get this. And now all terms will be constants. This is the constant, and obviously also these and these are also constants. So write this first as this 1 by c square t d2 t by dt square is constant, that is minus lambda square, and write this term from here 1 by phi d2 phi by d phi square as another constant, that is equal to minus k square. So then also you can write that these two terms cot theta by r square, this from these two terms also you consider from these two terms, that is from that is 1 by theta d2 theta by d phi square from here. Okay, then cot theta by theta d theta by dt, this will be d phi square. Here this will be d phi square. So 1 by theta, now also consider that 1 by this theta d2 phi by d phi square, then plus cot theta by theta d theta by d theta, that is equal to with also with this term there is another term, that is k square by lambda square sin square theta. K square, what was the k square? K square was this k square was this. Okay, k square was this. So k square, that is equal to minus n into n plus 1. You say it, you take it. Okay, now from this we can write 1 by theta d2 theta by d theta square plus cot theta no, this term, actually these two terms, sorry, these two terms. So once again we consider here, this is taken as minus lambda square. Okay, fine, and 1 by phi d2 phi by d phi square, that is equal to minus k square. Now these two terms, this term and this term, from here we write 1 by theta d2 theta by d theta square, that is here, and from here cot theta by theta d theta by dt. Actually we have taken here from here 1 by theta d2 theta by d theta square, that is here, and from here cot theta by theta d theta by dt, that is equal, that is here, and after that this term is minus k square by r square sin square theta. This term, you know, because 1 by phi d2 phi by d phi square is equal to minus k square. So this term, entire term, will give you minus k square r square sin square theta, and write it as this is another constant, that is minus n into n plus 1. Okay, from here you can write 1 by theta d2 theta by d theta square plus cot theta by theta d theta by d theta, that is just take it in this side. So k square by r square sin square theta and minus n into n plus 1. This is equation number 5. And from 2, that is equation number 2. This equation, from this equation, just substitute these values in this expression. So you will have 1 by r, this term 1 by r d2 r by dr square plus 2 by r dr by r plus then plus because you know the value of this is equal to this. So plus k square by r square sin square theta minus n into n plus 1 by r square, that and minus another k square by r square sin square theta is equal to minus lambda square. Just substitute these values, the value of these and the value of these in this expression. You will have the finally you will get this. And now just simplify 1 by r d2 by dr square plus 2 by r dr by r dr minus n into n plus 1 by r square plus lambda square, that is equal to 0. Okay, that is equal to 0. So from here d2r by dr square plus 2 by r dr by dr plus lambda square minus just lambda is taken, lambda square minus this lambda square is here, plus lambda square minus n into n plus 1 by r square into r is equal to 0. You can write this from this equation. So from equation number 3, that means here is the equation number 3, that means 1 by c square t d2 t by dt square is equal to minus lambda square. From this relation, this is here, you can write this once again. You will obtain d2 t by dt square plus lambda square c square t is equal to 0. So this will give you a solution for t is equal to a1 e to the plus minus I lambda ct. And again from the relation, again equation 4, that means equation 4 is here. This equation will give you d2 phi by d phi square plus k square capital phi is equal to 0. That is also here, that is also here. So this is equal to 0, and this will provide another solution for phi is equal to a2 e to the plus I k phi. And from equation 5, that is equation 5 is here. This is equation from this equation. From this equation, you can write equation 5 will provide you that d2 theta by d phi square d theta square plus cot theta d theta by d theta plus n into n plus 1 minus k square by sin square theta and into theta is equal to 0. And from here, you can write write it in this fashion, because these two terms, this term and this term, can be written as 1 by sin theta into d theta of sin theta cos theta. Because if you differentiate this first d2 to d theta by dt, that will give you d2 theta by d theta square, and this sin theta cancel each other. Then plus this sin 1 by sin theta is here, and this sin theta will provide you cos theta, that will give you cot theta. Here will be theta, so cot theta d theta by dt. So this will give you cot theta d theta by dt, and then n into n plus 1 minus k square sin square theta into theta is equal to 0. And from here, so you can write this relation. Okay, fine. And then cos theta, right? Cos theta is equal to mu here. Just substitute cos theta is equal to mu. Then minus sin theta cos theta, differentiation of this will give you minus sin theta d theta is equal to d mu. Or from here, d mu by d theta is equal to minus sin theta. So d theta by d small theta can be written as d capital theta into by d mu into d mu by d theta. That will provide you minus sin d theta by d mu. So so you can write from here that minus 1 by sin theta d theta by d theta is equal to d theta by d mu. Okay, this and in operator form, you can write 1 by sin theta 1 by sin theta d theta is equal to minus d mu. And now substituting these values in equation 9, that is in this equation, substitute these values. That will provide you minus d mu of minus sin square theta d theta by d mu plus n into n plus 1 minus k square sin square theta is equal to 0. Just substitute these values in this equation, just using this relation. So that from there you can write d mu of 1 minus mu square, because you know that sin square theta is equal to 1 minus cos square theta, and cos theta is equal to mu. So 1 minus cos square theta, then plus n into n plus 1 minus k square 1 minus mu square into theta is equal to 0. And you know that this is nothing but the Legendre associated Legendre equation. Okay, associated Legendre equation. So the solution of which is theta is equal to an pn k mu plus bn pn k mu, and using value of mu, theta is equal to an pn k cos theta plus bn pn k cos theta, and the solution is to be finite. Then if the solution is to be finite, then mu tends to be 0, and if mu tends to be 0, then bn tends to be 0, must be 0. Bn should be 0, and therefore theta is equal to an pn k cos theta. Okay, and you know the solution. We have to go to the first chapter, in which I have derived the solution of associated Legendre equation that has the form in this manner, that has the form like this. So here, using the boundary condition, you get theta is equal to this. Now if r is equal to, now you also consider that r is equal to s function of r to the power minus half. If it is if you take r is equal to this, then dr by dr is equal to just 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 differentiate this with respect to x, that will give you these and these, and finally these and these. Just do it. Nothing is very different and very new in this expression here. So d2r by dr square finally calculated as this. Okay, this. Now substitute these values in this expression that was found here. That was found here. Where that was found here. That is in this term. Oh, sorry. This is the yeah. This term that is found here. Yes. Here or here. Okay. Just substitute that values. So that expression is written once again here. So in this expression, write the substitute the values of dr by dr and d2 by dr on these relations, and that will give you if you once substitute this, that will give you these, and some substitution of these will give you these, and nothing is new here, nothing is different here. If these steps is written here, so no problems to understand. Just only come to this here. So this is d2 s by dr square plus 1 by r ds by dr, plus you can write this as lambda square minus n plus n plus, because you are splitting this n square n plus n, and this 1/4 is taken within this. So lambda square minus n square plus n plus 1 by 4 by r square s is equal to 0. From here d2 s by dr square is equal to 1 by r ds by dr plus lambda square minus, you can write this as n plus half whole square by r square into s is equal to 0, and this is also like this is also the Bessel equation. This has the form of Bessel equation, which has the solution SR is equal to b jn plus half lambda r plus c yn plus half lambda, because in this case n is replaced by n plus half. So in the Bessel equation it was n, here is n plus half. So we have to write here n plus half, jn plus half, and then yn plus half. This is the first kind of Bessel's function of first kind. This is the Bessel's function of second kind. So this is the solution for SR, and you know that R is equal to 1 by R to the power SR. So if you substitute the value of R in, or the value of S in this expression, that will give you R is equal to this. So this is the solution for R. So in this case we have obtained the solution for theta, for phi, for t, and for r, and the complete solution can be obtained by multiplying all these terms. Now go to the next section, that is solution of three-dimensional wave equation in cylindrical polar coordinates. In cylindrical polar coordinates, the wave equation has the form del 2u del t square is equal to c square del 2u del r square plus 1 by r del 2 del r plus 1 by r square del 2u del theta square plus del 2u by del square. This is the wave equation in cylindrical coordinates in 3 dimension. Now here is the process to solve it in separation of variable method. So you have to write u r theta z t is in this fashion. Now find out all the partial derivatives, the value of all the partial derivatives from this relation, that is the value of these, and these, and then substitute these values in this expression. Then you will have r theta z d2 theta by dt square is equal to c square, and all the terms. Yeah, all the terms there. Now just substituting dividing both sides by r theta z t and c square, that will give you this. And here the variables, therefore the variables are separated in this case, and all the terms should be equal to constant terms. So from here, like this 1 by c square t, d2t by dt square is equal to minus lambda square, these are constant, consider it, and then d2t by dt square plus c square lambda square t is equal to 0. That will give you a result, that will give you a solution for t as a1 cos lambda ct plus b1 sin lambda ct. And obviously another term is there. Consider that 1 by theta d2 theta d theta square, that is equal to minus k square, another constant. So from here you can write d2 theta by d theta square plus k square theta is equal to 0, and this will provide you another solution. We will provide you with a solution for theta, that is equal to a2 cos k theta plus b2 sin k theta. Now another term is there, 1 by z d2 z by d z square, that should be another constant, that is equal to minus k square taken. So d2 z by d z square plus k square z is equal to 0. That will provide you the solution z as a3 cos k1z plus b3 sin k1z. So from equation 2, now from equation number 2 is here. This is the equation number 2. This was equation number 2. This is equation. Just consider, see, look at here. This is equation number 2. So from equation number 2, or from this equation, you write this term 1 by r d2r by dr square plus 1 by rr dr by dr minus, you know that 1 by theta d2 theta by d theta square is equal to minus k square. So minus k square by r square. Then this term is equal to minus, this term is equal to minus k square, and we have taken this term is equal to minus lambda square. What are given? Yeah. So this is not, this is clear from this expression. This expression that this term is equal to this term with this, and this term is equal to this. And from here d2r by dr square plus 1 by r dr by dr minus lambda square is taken here. Okay. So minus lambda square minus k square by r square into r is equal to 0. You can write in this manner. Okay. Now then from here d2r by dr square plus 1 by r, d2 take lambda square on the side, then lambda plus square. So lambda square minus k square. So this should be a plus sign. This should be plus sign. Okay, because lambda is taken here, so lambda will be lambda square. So lambda square, then minus k square, then minus k square by r square into what? So this should be a plus sign. It has written mistakenly. It has written mistakenly. So that will be, there will be a plus sign. So that will be plus and that will be plus sign. So write k square alpha square as equal to, write this lambda square minus k square is taken as lambda square. Sorry, alpha square, right? This term lambda square minus k square is equal to alpha square. So then from this d2r by dr square plus 1 by r dr by dr plus alpha square minus k square by r square into r is equal to 0. This is another equation number 3, and putting, just substitute alpha r is equal to x, then dx by dr is equal to alpha, and then dr by dr can be written, find out in this manner, dr by dx into dx by dr, that will give you alpha dr by dx, and in this way d2r by dr square is computed here, and that will give you finally d2r by dr square is equal to alpha square d2r by dx square. So correction is made here. So just write these are plus sign instead of minus. So these will be plus, this will be plus. So now substituting the values of dr by dr and d2r by dr square in this expression, that is expression number 3, equation number 3, that will give you the expression number 3, that will give you alpha square d2r by dx square plus alpha by x, alpha into dr by dx plus alpha square minus k square alpha square by x square into r is equal to 0. And from here you can write d2r by dx square plus 1 by x dr by dx plus 1 minus k square by x square into r is equal to 0. Just you take alpha, you can write this. Just alpha, take as alpha as constant, common term from here, so alpha square will be there, 1 minus k square by x square. And all these alphas, this alpha square, this alpha and this alpha square will cancel, will be divided to 0. That is from here you can, this is equation number 4, and this is nothing but Bessel's equation, and which has the solution for r is equal to a4jkx plus a5ykx. Obviously jk is the Bessel's function for kth order for the first kind, and yk is the Bessel's function second kind for order number k. And just use the value of x, that is alpha. So a4jk alpha plus a5jk yk alpha. So now boundary condition, now a condition is to be imposed in this case also. When r tends to 0, then y k alpha should tends to be infinity, and then B4 should be 0. So B4 should be 0. Not in this case B4 not, it will be A5 will be 0. In this is a 5. Here is deterministic, however, it will be A5. A5 is equal to 0. Right, see here, it is A5. A5 is equal to 0. That means this term will not be there. Only term will be there is A4 JK alpha R. So if you write this, the complete solution then takes the form U R theta Z T is equal to A2 cos K theta plus B2 sin K theta, then A1 cos lambda ct plus B1 sin lambda ct, then A3 cos K1Z plus B3 sin K1Z, and then A4 JK lambda R. Just use the value, all the values uh, of here. Here is R. The values of R is here, capital R is here, and this value is for capital theta. This value is for capital T, and this value is for Z. So this is the complete solution of wave equation in three-dimensional cylindrical coordinates. And this is the end of this lecture. The end of this class. Students, we were requested to make modifications or make corrections which are like this. There correction should be there, that it would be a 5, and here there should be negative sign, positive sign instead of negative sign. That here will be positive sign, positive. This will also be positive sign. This correction, you should do this correction, and then all will be easier for you to understand. So this is the end of this lecture.